This is part 8 of the FACIT N4000 paper tape punch restoration, and if you've been watching the previous videos you know that I've got the punch pretty much up and running. I've got the tape reader working, but I'm left with this problem that when I try to power up the machine or enter any specific parameters, I get this pass message popping up, which I'm assuming is expecting me to enter a passcode. I can then only proceed by going into this mode where I can enter some digits. I don't know how many digits I should be entering, and obviously I don't know what the passcode is. I have found a workaround for this, so I can use the machine now, but just out of curiosity I wanted to look into the possibility of reverse engineering the machine to find out what the passcode is or how to bypass it properly. I haven't been able to find any technical information on this machine. I found an operator manual, and for some bizarre reason it does not mention this passcode feature, so I don't know if it's specific to this particular version of firmware that I have. But either way, I thought I'd do a quick introduction video to the way I go about reverse engineering firmware right from the start. I haven't actually done anything yet, and I'll do this as just a quick introductory video. If you are interested in seeing more videos on this aspect of reverse engineering firmware, then drop me a comment and I'll post some more as I progress. But it is a long and tedious process, so I won't bore you with all the details of the videos unless you're particularly interested in it. So the first thing I need to do, the first step in reverse engineering, is to gain as much access to the electronics as I can. So to that end, what I've done is produce an extender for the main board. So I'll just reposition the camera. Okay, so as you can see, what I've done is made up an extender. It's just an edge connector and a socket, and it just allows me to sit the board on the bench outside of the punch. It'd be a real pain having to try and operate this punch and see the keyboard with it on its back while trying to attach probes and the like to the main board. So obviously I need the CHAD box in place. If I do punch anything, I don't want the board and the workbench covering in CHAD. So step one is to see what we're actually up against. Now in this case it turns out that the system processor is an MC68701. So that's effectively an MC6801, except that instead of having a mask ROM, it's got an EEPROM. So under this sticker there's the usual window, and you can erase this if you want to. I won't do that because I don't have the code to put back into it. I also unfortunately don't have a reader capable of reading this device, so I can't read the contents of the firmware. But there's also an EEPROM over here. Now the way this device works is when the system boots up, and I'm not really familiar with this device, I've just printed off the user manual or the spec sheet. I've been reading through this, trying to pick up any information I can as to the basics of how this system might work. When the system boots up, while the reset line is low on this device, it monitors 3 pins, and the values or code on those 3 pins determines one of 7 modes that this thing can run in. And each of the modes puts the processor into a different operational mode, where the memory mapping and the way the chip operates is different. So in other words, it can use the internal EEPROM or an external EEPROM or a combination of the two. So this might not have any code in it at all. I know this does because I've read it out, and that's obviously the reason it's there. But I suspect this does have code in it simply because it has a version number on the sticker that's on it. In fact, this is a sticker I put on here because the original one I had to take off to see what the chip was. But because it's got a code printed on it, I suspect there's some firmware in this. I'm looking at various ways of reading this, but I haven't found a sensible solution yet. If any of you know how to read a 68701, then please let me know. So the first thing I need to do is to determine the mode this runs in. Now, having said that, one of the things I've already done, and I touched on this in a previous video, is that the spec sheet says that this has some retainable RAM in it, but I think what it means is it's battery backed RAM. It's not EEPROM. I didn't think it could be EEPROM based on the age of the chip, and looking at the spec sheet and application notes, it looks like what it actually is battery backed SRAM, and in fact on this spec sheet the pin 21 says it's VCC standby, and when you look at the standby function, it seems what it's supposed to do is if you want to have the RAM contents retained through power down, you have to apply voltage, a battery voltage, to this pin, and as long as that voltage stays above a certain level, the internal RAM contents are retained. And there's an internal flag that can be set to let the software know if the external battery voltage went below a certain value, in other words, whether or not the contents of that RAM can be trusted. So the first thing I wanted to do was to check to see if that was actually being used. So this is the only real testing I've already done. So if I now look at the battery voltage, so I know this is a ground connection over here. So the battery voltage is 3.4 volts. Now that indicates to me, bear in mind the age of this machine is the early 80s, so I suspect this has been changed. Looking at the solder connection, it definitely seems to have been replaced at some point. And I suspect that the way this system operates is it uses the SRAM as a non-volatile store for settings and parameters, because when I measure the battery backed voltage on here with the power off, so I'll turn the power off, and then measure the voltage on this pin, and as you can see there is no battery backed voltage being applied. So in other words, this is not connected to the battery backup battery. So in other words, it does not appear they're using that internal RAM as non-volatile storage, because if they were, they would be applying a battery backup voltage to that pin. That leads me to suspect that the parameters are being stored in here, but when I remove the battery and let this completely drain, I still have the same problem when I powered up again. So I think what happens is when the battery voltage is lost and this data is corrupt, I suspect it's loaded a default password from the either external or internal EEPROM, and that's the value I need to try and figure out. So the way I'm going to go about this is to first determine the mode that the processor is running in, and that's what I'm going to do in this video, and from that point on I will try to trap the entry into the part of the code that checks the password that's been entered, and part of that should show me where the actual passcode is being stored, and I can see what the value is. Try entering that into the keypad and see if that works, and then I can either decide whether or not I want to modify the EEPROM to just bypass the password, or see if there's a way I can reset the password so it doesn't keep popping up. Okay, so the first thing I need to do is look at how to determine the mode, and the way this works, as I said, the chip monitors 3 pins during reset, so the value on those 3 pins is read into the internal mode register on the rising edge of the reset, and those 3 pins are pin 8, 9 and 10, which I identified here as P20, 21 and 22, and it looks like the reason these are all just given P numbers is because their function is dependent on the mode the chip is put into when it powers up, and that's why I need to determine what that mode is, so I can look at what memory map is being used, and hence how to go about trapping various events and tracing through the code. What I'll do is I'll get the Agilent 1670G logic analyzer set up. I'll just configure it for now to look at these 3 pins and the reset, and then we'll capture the power up and see what the mode is that's being set. Okay, so I now have the logic analyzer set up. Hopefully you can hear me over the noise of the fan. And what I've done is I've connected the clock. I need to connect the clock because I'm running it in state mode, and I've connected a line to reset, and then I've connected the 3 inputs that select the mode on power up. So that is, I have the clock being fed to the analyzer, I have the reset line monitored, and then I have the 3 lines that are used to select the mode on power up. So what I'll do now is I'll reposition the camera so you can see the screen of the analyzer. I'll power up the punch, and we should be able to capture the mode input at the reset. Okay, so we're looking at the screen of the analyzer. I've got the master clock set as the J input, which is the clock input from pod 1, which is the one that we've got connected to the processor clock. I've created 3 inputs, PC0, PC1, PC2, which are the 3 mode input select lines. I've created a bus for those 3 lines as well, so we can look at the data value directly rather than having to look at the bit values. And I've created a reset input as well. So we can look at the waveform. The bottom trace, the blue trace, is the mode bus value. Currently it's showing 0 because we haven't run it. The 3 traces above that, the green, yellow and red, are the 3 PC inputs, and the top line is the reset input. So the way this works is when I set it to trigger, if we look at the trigger, I've created an input where, if we scroll across to look at the reset column, you can see that for term A I've set it such that it will trigger when the reset becomes high. In other words, we will capture the reset input value. That will occur one time, and so once I set this to run, then it will wait for the rising edge of the reset line. The punch is currently switched off. I will set the analyzer to wait for input, and I will now power up the punch. So what we can now see is we've captured the rising edge of the reset line, and it's at this point that the input values are saved to the mode internal select register, and as you can see we're getting a value of 5. So if we then look at the data sheet, we can see that the value of 5 gives us, let's have a look, it's non-multiplexed partial decode value. And then if we look at the description of that in the data sheet, we can see that mode 5 gives us 128 bytes of RAM, 2048 bytes of EEPROM, so that's using all of the internal RAM and EEPROM within that device, 256 bytes of external memory space. Port 3 is an 8-bit data bus, port 4 is input port address bus, that's acting as the address bus, and then we have 2 lines that are used for read-write control and input and output control. So in other words, this now gives us the memory access mode that the chip is running in, and then there is some more information in the data sheet that shows us what the particular memory map is for that mode. So if we look at the memory map for that mode, we can see that we have access to the internal registers, a gap that we don't use, the internal RAM, the external memory space, and then the internal EEPROM. So it looks like what's most likely happening here is that the external EEPROM is being used for some of the code, but the main system code is from the internal EEPROM, along with the interrupt vectors. So we now also know what the interrupt vectors are. That'll be our starting point for trying to get into the code. And this is what we'll use to try to capture information on the various operations that we're going to try and figure out. Okay, so that's it for this video. As I said, I won't show any more on this unless you're particularly interested. I may give an update if I find a solution. However, if you do want to see more of this process, then let me know.